In this lesson, we're going to take a look at some features of rational functions that are going to help us for the next lesson when we're going to go and actually graph these from scratch. So, what is a rational function? We've looked at radical functions. We actually have seen one rational function before. So let's define it. Definition. Oh, my spelling is not my thing today. So our definition of a rational function is that a rational function is defined as f of x equals g of x over h of x, where g of x and h of x are polynomials, and polynomials in x, as where they're g of x and h of x, so it's only polynomials with x variables. So some examples. Okay, so the first example you've actually seen before, which is y equals 1 over x. So that is our first example of a rational function. We also have x squared minus 4x plus 3 over x cubed minus 2x squared minus x, and we have, that would be our y equals, and y equals 1 over x to the 4th minus 1. So numbers are polynomials as well, so you can have just a single number in the top, or if it's in the bottom, it just ends up being a polynomial. So, what are some features we get with rational functions? Okay. So the first and most important feature of our rational functions that we're going to look at is the vertical asymptote. And again, you've seen this already for y equals 1 over x. So let's take a look at a specific rational function. We're not going to worry about exactly how to graph this whole thing just yet. That's going to be in the next lesson. So we're going to let f of x equal 1 over 2x squared minus 2. Okay, so let's factor that. It's a little easier to see what's happening when we factor it. So we factor out a 2, we get 1 over 2x squared minus 1, and then 1 over 2 times x plus 1, x minus 1. So the thing that we have with rational functions that we never had with polynomials or other functions we've looked at before is we have variables in the denominator. And as we remember from rational expressions and equations last year in Pre-Calculus 11, whenever we have a variable in the denominator, there are certain values that where x can't exist. And this restricts, when we look at this as a function, this restricts the domain of f of x. So where does f of x not exist? Well, we can't have 0 in the denominator, and the numbers, the x values that make our denominator 0 are positive and negative 1. So these are the and minus 1. So let's think a little bit now about what happens when we take a number and we try to divide it by, not by 0. We have no idea what happens when we divide by 0. We can't. However, if we try to divide by something that's really, really, really close to 0, what happens? So let's just go over to the side here a little. Okay. If I take 1 divided by 0.01. Okay, this is not related to the function, just thinking about what happens when we divide by really small numbers. I get 100. If I do 1 divided by 0.0001, I get 10,000. If I do 1 divided by 0.000001, I get 1 million. So the closer my number gets to 0, the bigger and bigger the result I get. If my denominator gets closer and closer to 0, the bigger and bigger my result is going to get generally. So if I did the same thing but with a negative number, I get 1 divided by negative 0.00001. I get the exact same thing, but negative. negative a million. So I'm actually getting smaller and smaller and smaller and smaller. So a vertical asymptote occurs when our function doesn't exist. And what the vertical asymptote causes around the vertical asymptote, the function is going to bend and then start going up, 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 or down, 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 as you get closer and closer and closer to the actual vertical asymptote. Because that makes, when you're getting closer to your vertical asymptote, you're making your denominator just get smaller and smaller and smaller and smaller. So we have here at 1 and negative 1, we draw vertical asymptotes as a line. So these are our vertical asymptotes. And they are caused where f of x does not exist. Okay? Does not exist, okay? There's one other thing that could possibly happen besides a vertical asymptote when f of x doesn't exist, but we're going to wait until the next lesson to take a look at what happens there. So if I sketch this graph, like I said, you don't necessarily need to know exactly how to do that right now, and it's not a very accurate sketch, it's just a sketch. Okay, we have what looks like kind of an interesting function that's been broken into pieces. Okay, so how we find these vertical asymptotes, remember, is the denominator of rational function equals 0 at VA, and numerator doesn't. So if the numerator and denominator are both approaching 0, something else happens, and we'll talk about that, as I said before, in the last lesson. So we've got this function. Let's take a look at the domain of this function. Generally, I'm not going to be asking you to find the range of rational functions, because it can actually get quite complicated. You have to look carefully at the different pieces. You can see here we're getting closer and closer to 0 as we travel in the plus x and the minus x direction. We'd have to calculate what the maximum is here. So it does get rather complicated. Okay, so we're generally just going to be asking for the domain. Range might be like a bonus question. So the domain is all x's that are elements of the real numbers such that x is not equal to 1 or negative 1. And we can do it fancier. You can just say x is not equal to 1 or negative 1 as your domain. Okay, so next you can see what our function does right here along the asymptotes. It kind of takes off for infinity in the y direction. It takes off for positive or for negative infinity. Now, we can also see that something similar is happening in the x direction. We seem to be kind of taking off, and we're sort of approaching 0, but it doesn't look like we're actually going to get there. This is called a horizontal asymptote. And horizontal asymptotes are different. Vertical asymptote is caused by the function exploding, blowing up. It doesn't exist anymore, so it's going to cause a whole break in the domain. Horizontal asymptotes are just what happens at the ends of your function. Is your function approaching, is it just getting bigger and bigger or smaller and smaller? In that case, it probably doesn't have a horizontal asymptote. If, however, it is approaching, like our function we're looking at up here, if it's approaching a fixed value, so in this case, this one will, if you keep drawing it and drawing it and drawing it, it will get really, really close to 0. So this is a horizontal asymptote. So these occur when x approaches, or you can say approaches, it never actually will get to positive infinity or negative infinity, and y approaches a particular value, rather than just getting bigger and smaller, or rather than going back and forth and back and forth. Okay. And the other difference between horizontal asymptotes is that the function cannot cross vertical asymptotes because it's outside the domain. It does not exist there. So you can't have a point of your function occurring within a vertical asymptote. Okay, but it can cross horizontal asymptotes because the horizontal asymptote is really just a description of an end behavior of the function, what's happening when you go really, really far, where it's approaching a fixed value. Okay, so we're going to take a look first at, so as we can see, if we look back at our function, we can see, if we see the graph of a function, we can look and see what the values are approaching as they get really far, and we can tell what our horizontal asymptote is this way. So for the graph of the function above, our horizontal asymptote is at y equals 0. Okay, so we're going to take a look at how to find that algebraically. Vertical asymptotes are a little easier to find algebraically because vertical asymptotes you just have to look at the denominator. For horizontal asymptotes, you have to look at both. And I'm going to abbreviate V dot A for vertical asymptotes and H dot A for horizontal asymptotes. So find the horizontal asymptotes for the function y equals 3x cubed minus 2x squared plus 1 all over 5x cubed minus 17x plus 39. What a lovely function. Okay, so what we're going to try to look at, so let's say as x goes to infinity, gets bigger and bigger, positive or negative, we are going to call it, and any rational function that's just a polynomial over a polynomial will always have the same horizontal asymptote for positive and negative infinity. So we can just look at positive infinity. So as x approaches positive infinity, we will call it b. Okay. So what do I mean by b? B is just a really, really scary big number, like huge, like the number of atoms in your entire house, something hugely, gigantically big. Okay, so let's let x go to infinity. So x goes to infinity, and so f of x is going to go to, well, let's take a look here. If we take a look at our function and we look at the very first terms, as I get really, really big, cubing a number is going to become so big that squaring a number just is like a rounding error. So if you want to try it, try doing 100 to the third power versus 100 to the second power and see the difference. Then try doing 1,000 to the third power and then see the difference between that and 1,000 to the second power. And then 1,000,000 to the third power versus 1,000,000 to the second power. And what we can see is that the bigger and bigger the number gets, the more and more insignificant the lower degree terms get. So when our function gets really, 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 really big, we get 3b cubed over 5b cubed, because the other ones are just basically like a little rounding error. It doesn't matter if you have like 17 quadrillion and then you have like a few 100,000, that's not going to make a huge difference when you divide. So the bigger and bigger you get, the more and more we can think of this as just the highest degree terms. So what happens is we get bigger and bigger and bigger and bigger. These, the big over the big, is going to stay big to the cubed over the big cubed, are going to continue to cancel out no matter how big we get. So our horizontal asymptote is y equals 3/5 for this particular function. Okay? So what happens if we wanted to see what happened when we approach negative infinity? It would work out the same because we'd be dividing by a negative and by a negative. So let's take a look at another example. Okay, we have f of x Okay, so we're going to find the horizontal asymptotes. For, we have our f of x, which is 3x to the fourth minus 2x squared plus 1 over x to the fifth minus 4x cubed plus 2x. And then we're going to look at g of x, where we have x to the fifth minus 4x cubed plus 2x, and then 3x to the fourth minus 2x squared plus 1. So again, we're really only looking at the highest degree terms. Okay, so let's take a look at f of x. So for f of x, as x goes to infinity, f of x goes to 3 big number to the fourth over big number to the fifth. Okay, we can cancel b to the fourth with a b to the fifth, and we get 3 over b. Well, as b gets humongous, that 3 isn't going to make any more difference than a 1 or a 100 or any other number. So this is going to go to 0. Okay, so our horizontal, note, it's not going to actually get there because you can't divide your way to 0. We talked about that a little bit when we were doing geometric sequences. But it does give us a horizontal asymptote at y equals 0, which means the value of the function will continue approaching 0. Here we have, for g of x, as x approaches infinity, we get f of x. Again, we're only looking at that highest degree term for the numerator and denominator, equals x to the fifth, sorry, b to the fifth. I don't know why I wrote x. B, oh, it's wrong in my notes. That's why I wrote it. You learn something new every day. 3b to the fourth, and this is going to give us a b over 3. And that is going to go to positive infinity. So if you get infinity, as x goes to infinity, big number is just going to infinity divided by 3, which is still infinite. What this means is essentially that the function will just keep getting bigger and bigger and bigger, like a quadratic or like a cubic or any of those other kinds of functions. And so this one, we would say there is no horizontal asymptote, but we have figured out what the end behavior is at positive infinity, which is that it's getting bigger and bigger and bigger. Okay. So it looks like, now let's just take a quick look back. It looks like one thing is happening when we have the highest degree term in the numerator and denominator has the same degree. Something is happening when the highest degree term is in the denominator, and something is happening when the highest degree term is in the numerator. And this actually can translate into a list of rules. So if you'd like to see the rules, please see page 176, which gives you you can always use this calculation involving b to work it out. However, if you prefer to memorize rules, there are some lovely rules for you to take a look at regarding what the degree of the highest degree term is. You still have to look at the highest degree term, but then you can figure it out depending on whether it's in the numerator, denominator, or whether it's the same. Okay. The next part of rational functions is actually something that you've done before with a lot of other different kinds of functions. So we're going to take a look at intercepts of rational functions. Okay, so we find intercepts of rational functions the same way we find intercepts of any other functions. So our y-intercept occurs where x equals 0, just like a linear equation, just like a quadratic equation. So x-intercepts, they actually work the same way as well. So x-intercepts occur where y equals 0. But the thing we have to think about is where exactly, what values, when we have a algebraic fraction or a rational function, where are the values that are going to actually give us the y equal to 0 but not existing? So we have f of x equals g of x over h of x. So we have a polynomial in the numerator, polynomial in the denominator. So our x-intercepts are going to occur where g of x is equal to 0, because a fraction is 0 when its numerator is 0. Okay, so what follows is for f of x to be 0, we just need the numerator to be equal to 0. We also, in order to have an x-intercept, the function has to exist at that point. So in order to actually have an x-intercept there, h of x has to not be 0 as well. Okay, so this is an and. These both must be true. Okay, so let's see how we would find the intercepts of a rational function versus any other type of function, just to make sure we're okay with that. So we're going to find intercepts for f of x equals x squared plus 1 over x cubed minus 2x. Okay, so let's start in with our y-intercept. Okay, well, f of 0 equals 0 squared plus 1 over 0 cubed minus 2 times 0, which gives us 1 over 0. Uh-oh, I thought the y-intercept had to exist when I plugged in 0. Well, not with a rational function. So rational functions don't always have y-intercepts. In this case, we can see we get something that's undefined. So our y-intercept doesn't exist. We made the added discovery that actually, since 0 makes the denominator 0 and not the numerator, we have a vertical asymptote at x equals 0. And this is why we generally find vertical asymptotes first, because if you know there's a vertical asymptote at x equals 0, you don't have to bother trying to find the y-intercept, because you know it's not going to exist. Our x-intercept, well, we're going to take just the numerator and set it equal to 0. So we get x squared plus 1 equals 0. Then we're going to solve. We have x squared equals negative 1. And then there are no real solutions here. So just remember, if we're saying if our solving our problem requires us to divide by 0, then that is undefined. If we are trying to take the square root of a negative, that generally we refer to as no real solutions. Okay, so there are no x-intercepts. And you can see that it's possible then to have a quite complex looking function that actually doesn't cross the x or y axis at all. Like our first example that we saw of the graph of a radical function, that one actually did not intersect the x-axis at all.